All right, welcome to the deep dive. Today we've got something, well, pretty fundamental. For a philosopher especially, this is going to get right at those really basic questions we love to ponder. We're diving into mathematical Platonism.
Yeah, that's it. And, we're really focusing in on this idea, this whole perspective about what math is, really. What are those truths it talks about? What are those objects it describes? So, yeah, for a philosopher, this is where things get interesting, like existence, abstraction, knowledge, all those big ones.
Okay, so let's start at the beginning. The Stanford Encyclopedia of Philosophy, they say mathematical Platonism basically comes down to this. There are these abstract math objects, numbers, sets, you name it, and they exist completely independent of us, our thoughts, our language, our whole existence. It's all irrelevant to whether these mathematical things are out there.
Precisely. And, the analogy they use is really helpful, especially from a philosophical viewpoint. Just like we accept that electrons exist, or those far-off galaxies, whether or not humans are looking at them, math Platonism says the same thing about the number 2, or like the set of all integers. It's like they're just there. And the key here is that the truths about these mathematical things are determined by what they are, just like how the truths about physical things are based on their properties.
And that leads to a pretty wild implication, doesn't it?
Yeah.
That math truths aren't something we just made up. They're discoveries waiting to happen. It's almost like a scientist uncovering a law of nature rather than like a politician making up a new law. This immediately throws into sharp relief how we might conceive of other forms of knowledge.
Yeah.
So the seemingly simple act of saying 2 plus 2 equals 4 carries a heavy philosophical weight, implying the real existence of these abstract entities 2, 4, and the operation of addition if we take the language at face value.
Absolutely. And in this deep dive, we're going to, well, first, carefully define what mathematical Platonism actually is. Then we'll get into the big arguments for it, followed by, of course, the big arguments against it. And then, we'll look at some other viewpoints that try to make sense of all this. Our goal is to give you a clear, solid understanding of this whole debate.
Sounds good. So let's get specific. What makes up mathematical Platonism? The encyclopedia breaks it down into 3 core parts: existence, abstractness, and independence.
Exactly. Let's take those one by one. First, existence. This just means that, mathematical objects actually exist.
Yeah.
Sometimes they formalize it by saying there's some X, and that X is a mathematical object. But the big philosophical question here is how they exist, which leads us to our next point.
Abstractness, right. These mathematical objects, they aren't just floating around in space or time. Like you can't bump into the square root of -1 or check out what a group is made of, chemically speaking.
Exactly. Abstractness means they're not tied to space or time. And because of that, they can't cause anything in the physical world. It's a fundamental difference from something concrete, like a chair, or even a tiny particle, like a quark.
All right, so these math objects exist, and they're abstract. Now for the tricky part, independence. What does it really mean for these objects to be independent of us? Independent of our minds, our language, how we think, and even how we do math?
This is where it gets really philosophical, like the encyclopedia points out. You might initially think, well, would these math things still exist if we didn't? And yeah, most philosophers would probably agree with that. After all, we use math to think about all sorts of situations, even ones without people. But the encyclopedia hints that when it comes to Platonism, independence goes even deeper than that. We'll unpack that more later. For now, just know that it means these mathematical things are profoundly objective. They just are, regardless of us.
And it's important for philosophers to note that, this current idea of Platonism, it's not exactly the same as what Plato himself said about forms. Sure, it's inspired by that whole concept of eternal abstract things, but modern Platonism stands on its own, metaphysically speaking.
Yeah.
We're not trying to interpret Plato here.
Exactly. And another important point is this. Contemporary Platonism is mainly about metaphysics, not epistemology. Earlier versions had a lot to say about how we can directly know these abstract things, but most Platonists today, they don't necessarily talk about some special, math intuition or anything like that. And one more thing the encyclopedia clears up is that the necessity of mathematical truths, whether they have to be true, that's not actually part of defining contemporary Platonism either.
Okay, so why should we care? What's the big philosophical deal with mathematical Platonism? It can't just be a debate for specialists.
Not at all. If it's true, it affects a bunch of other areas of philosophy. First, it challenges physicalism, the idea that reality is only made of, well, physical stuff. If numbers, sets, and all those mathematical objects exist independently in some non-physical way, then reality is much bigger than just the stuff physicists study. Wow, so the seemingly abstract world of numbers and sets could fundamentally alter our understanding of what reality even is. That's mind-blowing.
Right. It opens up this whole realm of non-physical things. And then there's the problem it causes for those naturalistic theories of knowledge. How do we know anything about these abstract things that can't interact with us?
That's the big question. We obviously know a lot of math. If Platonism is true, it means we know about things that are totally beyond our reach. This raises some massive questions about how we know anything at all, and if a big problem for theories that say knowledge comes from observation and cause and effect. So, if there's no way for these mathematical objects to interact with us, isn't it just a bizarre coincidence that our mathematical intuitions and deductions seem to align so perfectly with this independent realm? That feels deeply unsatisfying as an explanation.
But the encyclopedia also mentions how successful math is. It's not just some, side hobby. It's the basis for so much of our scientific and technological understanding.
And that's really important for a philosopher to consider. Math isn't just random symbols and rules. It works. It's essential for almost every science. So if we end up leaning towards a Platonist view of math, we can't just ignore it. Rejecting the very basis of something so intellectually successful would be, well, pretty tough to swallow. We've got to deal with what it means.
So Platonism is the full package: existence, abstractness, and independence. But the encyclopedia also talks about object realism. How is that different from Platonism?
Think of object realism as a kind of like minimalist math realism. It agrees with Platonism on the first two parts, that abstract math objects exist and they are abstract. But it doesn't go all the way with independence. So just to be super clear, that idea of independence, that these abstract objects are totally separate from us, that's what makes object realism turn into full-blown mathematical Platonism.
So you could believe in object realism without being a full-on Platonist.
Absolutely. By leaving out independence, object realism avoids some of the more, let's say, radical stuff from Platonism, the metaphysical and epistemological parts. A philosopher who leans towards physicalism, they might be okay with non-physical objects if they depend on or can be reduced to physical stuff, or if they're like creations of the human mind. The mystery of how we know about things we've, in some sense, made is less acute.
Got it. Can you give us an example of a philosophical view that's object realist but not totally Platonist?
Sure, traditional intuitionism is a good one. Intuitionists, they believe in math objects, but they say these objects actually depend on what mathematicians do, on their mental constructions. So the objects exist, but as mental things. And they're abstract because, they're in the mind and not the physical world. But they definitely aren't independent of us. So it fits object realism, but it's not Platonism. And the encyclopedia says we'll see more of these kind of in-between views later on.
Interesting. Now, the encyclopedia also brings up truth-value realism. What is that, and how does it relate to all this?
Truth-value realism basically says that every well-formed math statement is either true or false, objectively, and that's regardless of whether we know it's true or false, or whether it fits with our current theories. And it usually includes the idea that most of the math we accept as true is actually true.
So this is about whether math statements are true, not necessarily whether the objects they talk about exist.
Exactly. It's a metaphysical view about the nature of math truth, but not necessarily about what math is made of, ontologically speaking. Platonism offers a pretty natural explanation for truth-value realism. I mean, if math is about objects with their own properties, then those statements about them would be objectively true or false, right? But logically speaking, you don't need Platonism for truth-value realism.
So you could believe in truth-value realism without being a Platonist.
For sure. The encyclopedia even says some nominalists, those who don't believe in abstract objects at all, can still be truth-value realists, at least for basic math like arithmetic. They might say a statement like, there are prime numbers between 10 and 20 is true, even though they don't believe in numbers as these abstract things. It requires translating math language into a different philosophical language, one that doesn't use abstract objects, but it's a philosophically coherent position.
That's a little mind-bending at first. If you believe in a more direct connection between language and reality, how can something about numbers be true if you don't think numbers exist?
Well, the key is to remember that the language mathematicians use and the language philosophers use to analyze math, those are different. A nominalist might say, hey, we can translate that statement about prime numbers into our own language, one that doesn't need abstract objects, and it would still be true. And the other way around, the encyclopedia notes, you could be a Platonist and still wonder if every math statement has a definite truth value. Maybe some parts of math are just inherently fuzzy.
That's an important distinction, showing that this debate isn't just about what exists, it's also about the nature of truth in math. The encyclopedia even suggests maybe we should focus more on truth-value realism, than Platonism. Why is that?
The argument is that arguing about Platonism can get messy with those ontological questions about what exists, and maybe we'll never get a clear answer. But with truth-value realism, we're dealing with the objectivity and certainty of math knowledge, and some philosophers think that's even more fundamental than whether those math objects actually exist.
Okay, so we've covered definitions and some related philosophical positions. Now let's look at how Platonism affects how math is actually done. The encyclopedia talks about mathematical significance and working realism. What's that about?
Working realism is basically how lots of mathematicians do math. It's like they're assuming Platonism is true, even if they don't necessarily believe it. They use language and methods that seem to require those mathematical objects to exist.
Can you give us some examples of these Platonistic methods?
Sure. Like, they use classical first-order languages that seem to directly refer to math objects. They use classical logic, which relies on things like the law of excluded middle instead of more restrictive logics. They're fine with non-constructive methods and axioms like the axiom of choice. They use impredicative definitions. And they generally believe in what's called Hilbertian optimism, the idea that every math problem can be solved. Think of impredicative definitions like trying to define all the books in the library by including the very definition you're currently reading as one of the books. It creates a kind of circularity that some find concerning.
So working realism is a way of doing math. Does that mean everyone who does math this way is a philosophical Platonist?
Not at all. It's more about methodology, how they approach their work. It doesn't mean they believe in Platonism or think it needs to be philosophically justified. A mathematician could be a working realist and have completely different philosophical ideas about what math is.
But the encyclopedia does say Platonism can support working realism, right? If you think mathematical objects exist independently, then using language that refers to them and logic that works on that independent reality makes sense.
You got it. If math truths are discoveries about an objective realm, then why would you limit yourself to constructive methods? If a proof shows something true about that realm, even if it's non-constructive, it's totally legitimate. Even Gödel argued that impredicative definitions are okay if the things being defined actually exist independently. And that whole idea of an objective mathematical reality, it gives some weight to Hilbert's optimism, that idea that every math question has a definite answer out there.
But the encyclopedia is careful to say that working realism doesn't automatically mean you're a Platonist. You could use that kind of Platonistic language in those methods without believing in that whole independent realm.
That's super important for a philosopher. The language of math, you can understand it in different ways. It doesn't force you to believe in mathematical objects as real independent things. And even if you take the language literally, it might support object realism, the existence, and abstractness. But to get to full-on Platonism with independence, you need a separate argument for that.
Right. So all this brings us to the big question. Why should a philosopher believe in mathematical Platonism? Let's get into the Phrygian argument for existence. The encyclopedia calls this the most important argument for it.
This argument from Frege, it gives a strong framework for arguing that those mathematical objects actually exist. It's based on two main premises. The first is classical semantics. This is the idea that the language of math, when you take it literally, it's referring to and quantifying over mathematical objects. So the seemingly simple act of saying 2 + 2 = 4 carries a heavy philosophical weight, implying the real existence of these abstract entities, 2, 4, and the operation of addition if we take the language at face value.
Just to be clear, what does that word purport mean here?
Purport here means that for a math sentence to be true, the parts of that sentence have to actually refer to or quantify over math objects like the grammar suggests they do. If they don't actually refer to those things, the sentence can't be true.
Okay, so the first premise is that math language works as if it's talking about math objects. What's the second one?
The second premise is just truth. Most of the things we accept as math theorems are actually true. Seems pretty hard to disagree with that if you're serious about math.
I'd say so. So how do those two premises lead to the conclusion that math objects exist?
Here's the logic. We accept lots of math theorems with terms that seem to refer to math objects. That's premise 1. And those theorems are mostly true. That's premise 2. But if those terms don't actually refer to existing math objects, those sentences can't be true. That's from classical semantics. So those math objects must exist for those accepted theorems to be true.
That's pretty straightforward and convincing, at least at first glance. But it seems like both of those premises, classical semantics and truth, could be challenged. How do people defend them? Let's start with classical semantics.
The main defense is it's how plausible it seems at first glance. If you look at math language, it really does look a lot like ordinary language, how we talk about everyday objects. The encyclopedia uses this example. Evelyn is prim and 11 is prime. They seem to have the same grammatical structure, right? Subject, verb, object. And most linguists agree with that basic analysis. It's really a description of how mathematicians and people who use math actually use the language.
But the encyclopedia mentions that nominalists and other anti-realists, they don't buy this simple semantic analysis.
Of course, they would need to come up with another way to understand math language, one that doesn't involve math objects, even though it looks like it does. And this alternative would need to convince not just philosophers, but also linguists and those who study language, people who don't necessarily have a stake in the philosophy of math debate. It's a tall order to overturn that seemingly natural interpretation of math language.
Right. Okay, what about the second premise, truth? How do you argue that those math theorems are actually true?
The encyclopedia gives three main approaches. The first is logicism, championed by Frege himself. Logicists try to show that math truths actually come from logic and definitions, and since logic is supposedly fundamental, this would mean math is on solid ground, truth-wise.
And the second approach?
That's the indispensability argument, mainly from Quine and Putnam. They say math is crucial for our best scientific theories. If those theories are probably true about the world, then the math they use must also be true.
Makes sense. Science relies heavily on math. So if science is giving us a true picture of reality, the mathematical tools it uses must be reliable and true too. And the third way to defend the truth of accepted mathematical theorems.
The third one is mathematical naturalism. This says we don't need to appeal to stuff outside of math, like logic or science, to justify it. Math has its own internal standards for justification.
How do those internal standards work?
Well, one way is to focus on how mathematicians think about their results. They accept them as true. The idea is that they're justified in doing so because of rigorous proofs and peer review, and that acceptance means they believe the theorem is true, and that the content of that belief is the literal meaning of the theorem. Therefore, we're justified in believing that accepted mathematical theorems are actually true, literally.
But the encyclopedia points out that fictionalists, they might disagree here. They might say you can accept a math statement as a useful tool without actually believing it's literally true about a world of abstract objects.
Exactly. Fictionalists offer other interpretations of math language and practice that don't require that same ontological commitment, that belief in those objects.
Now, the Phrygian argument is often talked about with ontological commitment. Can you explain that connection and why it's relevant to Platonism?
Ontological commitment, following Quine, it's basically about what a sentence or a whole theory has to assume exists for it to be true. If you accept classical semantics, then lots of math sentences, with their specific terms like the number 2 and their quantifiers like there exists, they seem to be saying that math objects exist. And if those sentences are true, as per the truth premise, then those objects must exist to make them true.
So if you agree with Quine's idea, then accepting math truths based on a straightforward reading of math language means you have to accept the existence of math objects.
That's the main idea. But remember, not everyone agrees with Quine's criterion. Some say using those specific terms and quantifiers doesn't automatically mean ontological commitment, or that we need to modify or even reject Quine's idea entirely.
And the encyclopedia mentions that the Phrygian argument can be made without using that phrase, ontological commitment. So it might avoid some of the criticisms specifically aimed at Quine.
That's right. The core of the argument is about how we seem to be successfully referring to things with math language in statements we believe are true. The philosophical debate then becomes, is that conclusion that those math objects exist enough to establish full-blown Platonism?
Because, as we said, existence is just one part of Platonism. We still need abstractness and independence. How do you go from saying these things exist to saying they're abstract and independent of us?
The encyclopedia notes that the abstractness of math objects is less controversial. Not many people argue that numbers or sets are concrete things in space and time. One way to support abstractness is to look at what pure mathematicians do. They don't worry about the physical stuff or causal powers of the things they study. If numbers or sets were located somewhere or could cause things, that would be a huge gap in their research. It suggests those math objects are abstract.
Yeah, that makes sense. It would be weird if number theorists were trying to pinpoint where the number 7 is located. What about going from existence and abstractness to independence?
That's where it gets tough. The encyclopedia even dedicates a whole section later to different interpretations of independence. It's often seen as the key difference between general math realism and full-on mathematical Platonism.
So we've got this free gene argument pushing us towards accepting the existence of abstract math objects. But there are some serious objections to mathematical Platonism. Let's look at those. Starting with the problem of epistemological access. This is also known as Benaceref's problem.
Benaceref's problem, basically, is how can we, as physical beings in a physical world, know anything about these abstract mathematical objects that can't affect us and exist independently? Field gave us a more refined version of this objection, a trilemma with 3 premises.
What are those premises?
First, mathematicians are generally right when they say a math statement is true based on a good proof. It's very likely to be true. Second, for our mathematical beliefs to be justified knowledge, we need at least some possible explanation for why we're so good at math. And third, this is the big challenge to Platonism. If Platonism is true, we can't explain our accuracy in math because those Platonic entities are causally isolated from us.
I think even people who like Platonism would agree with the first 2 premises. It's the third one that's really up for debate. Why does Platonism supposedly make it impossible to explain why we're good at math?
Field argues that any good explanation for why we're accurate in some area has to involve some kind of cause and effect relationship between us and the things in that area. Since Platonic math objects are outside of space and time and can't cause anything, that kind of connection just can't exist. So how we're so good at math would be a total mystery, like we're just lucky guessers. That undermines any real justification for our math beliefs.
But the encyclopedia says that this idea that you need a causal connection for accuracy, that's been challenged in responses to Benaceref's problem.
You're right. Some philosophers have tried to give different, more basic explanations for our mathematical reliability that don't rely on interacting with a Platonic realm. They suggest that maybe it's the internal consistency of math systems, the logical relationships between math statements, or even evolutionary pressure that favors logical thinking. These could all play a part in making us good at math without needing that causal link to abstract objects. Lenebo, in the encyclopedia entry, even critiques Field's argument for the causal isolation of math objects. And the reason these alternative explanations are so important is that if we can't offer a plausible account of how we reliably access mathematical truths under Platonism, it really casts doubt on the entire framework. These minimal explanations are attempts to bridge that seemingly impossible gap.
So the epistemological objection is a big one for Platonism. But it doesn't necessarily disprove it because people are still working on explaining our math knowledge. What's the next big objection? The encyclopedia mentions another metaphysical one, also from Benaceref.
This one's different. It focuses on what math objects actually are, especially natural numbers. Benaceref thinks numbers are basically defined by their place in a structure, like that infinite sequence of natural numbers. So being the number 3 just means being after 2, being a prime number, stuff like that. There's no special essence to 3 outside of its relationships.
And from this, he comes to a pretty radical conclusion, doesn't he?
He says that if numbers are just about structure, with no identity outside of that structure, then they're not real objects. His reasoning is that any real object has to have some properties beyond its place in a system. Structures are about relations, but the things in the structure, they can't just be placeholders. They need some kind of identity beyond their role in the structure.
That's a big claim. It challenges how we usually think about numbers. But the encyclopedia says both parts of this argument are debated in the philosophy of math.
Yeah, many structuralists agree with the first part, that numbers are fundamentally structural, but they disagree with the second. They say objects can be fully defined by their structural properties and relationships. And then you've got logicists and neologicists who usually deny the first part. They say numbers are tied to how many things are in a collection or to the extension of a concept. And then there are some who actually agree with Benaceref's second part. They think real objects need more than just structural properties. It's a complicated issue with lots of different views.
Are there any other big metaphysical objections the encyclopedia mentions?
It briefly talks about Goodman's radical nominalism and his principle of nominalism. This says that if 2 things are made of the exact same basic parts, then they're actually the same thing. It's like a stronger version of the set theoretic idea extensionality. Goodman used this to try and get rid of sets, which are fundamental to a huge amount of modern math.
But the encyclopedia says Goodman's nominalism isn't popular nowadays. Why not?
Mostly because set theory is so useful and successful. It provides a unified, consistent foundation for tons of math concepts and theories. So rejecting sets entirely, like Goodman did, that's not a common view anymore.
We've looked at the arguments for Platonism and some big objections to it. Now, the encyclopedia talks about views that fall between object realism and mathematical Platonism. These are lightweight forms of object realism. What are they trying to do?
These views agree with the first two parts of Platonism, that abstract mathematical objects exist, which is object realism, but they're not so sure about the third part, the independence thesis. That's the one that says these objects are just as real as physical objects, existing in their own separate realm. These lightweight realists want to be realists about math objects without fully committing to the strongest, potentially most problematic version of Platonism.
And it seems like how they understand the independence thesis is key here. We talked about counterfactual independence before.
Right. Counterfactual independence means math objects and truths would still exist even if we didn't. The encyclopedia suggests that most analytic philosophers probably agree with that. We use math all the time to think about situations without people, and we do it pretty easily. That suggests math truths are independent of our existence. If that's all independence meant, then object realism would basically be the same as Platonism.
But the encyclopedia argues that the meaning of independence in Platonism is stronger than just counterfactual independence. It's more like robust independence.
Exactly. Robust independence says that math objects are as real as physical objects, metaphysically speaking. The analogy is that numbers and sets exist apart from us in the same basic way as electrons and planets, in their own objective realm. The lightweight views usually don't go for this strong version of independence.
So what are some examples of these views trying to find a middle ground? The encyclopedia talks about plenitudinous Platonism. That sounds pretty big.
Plenitudinous Platonism, especially Balaguer's version, has this strong plenitude principle. If a math object is possible, meaning its existence doesn't contradict basic math principles, then it actually exists. For example, the continuum hypothesis, you know that one, it's independent of standard set theory. A plenitudinous Platonist might say there's one universe of sets where it's true and another where it's false, and neither is more real than the other. This is different from typical Platonism, which usually says there's just one universe of sets where every math statement has a definite truth value, including the continuum hypothesis.
So what's the point of this math multiverse idea?
One reason is epistemological. If every consistent math theory describes some real collection of math objects, then knowing math might be easier. If you show a theory is consistent, you know it's true in at least one of these math universes. But there are criticisms. Like, how can we even refer to specific math objects if there are so many of them? And can you even define the plenitude principle clearly?
And the encyclopedia mentions another kind of plenitudinous Platonism from Linsky and Zalta, based on their object theory.
Right. They say traditional Platonism messes up by thinking about abstract objects too much like physical ones. They assume there's a kind of sparseness in the realm of abstract things. Their theory has a general principle. For any well-defined group of properties, there's an abstract object that has exactly those properties. They think this is a better way to understand the relationship between our thoughts and abstract objects, and it leads to a lot more abstract entities than traditional Platonism allows. But of course, their theory has also been debated.
Another interesting idea they discuss is lightweight semantic values. How does this fit into the whole independence debate?
The basic idea is to start with object realism and classical semantics. Those math terms do refer to abstract objects, but they argue that maybe it doesn't take that much for a math term to have an abstract object as its meaning, its semantic value. Maybe all it needs to do is contribute to the truth values of sentences it's in. This allows for non-eliminative reductionism. A term might refer to an abstract object, but that reference is ultimately based on more basic facts that don't directly involve that object.
Can you give us an example of these lightweight semantic values and that non-eliminative reduction?
They use the example of directions defined by parallel lines. Direction might seem like it refers to an abstract object, but maybe statements about directions are ultimately true because of the relationship of parallelism between lines. We don't actually need directions as separate things. Linnebaugh argues that this supports counterfactual independence because those parallel lines would define the direction even if we didn't exist. But it doesn't necessarily mean robust independence, because a direction doesn't affect the physical world the same way a physical object does.
Okay, and finally, the encyclopedia looks at inspiration from Aristotle, offering two ideas relevant to all this.
The first is Aristotle's idea of potential versus actual existence. He thought natural numbers were potentially infinite. You can always imagine a bigger one, but not actually infinite as a complete set, because that would need an actually infinite physical world. Modern math, of course, accepts actual infinity partly by rejecting that need for a physical thing to correspond to it. But that idea of potential existence is still around in some set theories, like the iterative conception, which focuses on how sets are built up over time. This suggests a different way of existing for sets compared to, unchanging physical objects.
And the second Aristotelian idea.
That's ontological dependence or derivative existence. This is the idea that the existence and properties of mathematical things might depend on non-mathematical stuff. For instance, some argue that numbers might be grounded in facts about provability in a formal system, or in possible structures, or even in groups of things that show numerical properties. Others say sets depend on their members for their existence. These views offer ways to be a realist about math without needing those Platonic objects to be fully independent. They might depend on something else for their existence.
Well, that was a really thorough look at mathematical Platonism and all the different ideas around it. To wrap up, can you summarize the main points we've covered?
We started by carefully defining what mathematical Platonism is, focusing on those three core parts: existence, abstractness, and independence. Then we looked at the Phrygian argument as a reason to believe in math objects. We dealt with some major objections, especially Benacerraf's arguments about how we can know these things and what they are. Finally, we looked at different views that try to find a middle ground between Platonism and nominalism, focusing on how to understand independence and the possibility of being a realist without going full Platonist.
It really shows the tension at the heart of this debate, doesn't it? Math language and the objectivity of math truth seem to point towards realism, but accepting a whole world of abstract objects that can't affect us and exist on their own and figuring out how we know about them, those are big hurdles.
Definitely. It's a deep, ongoing discussion that goes to the very core of how we understand reality and knowledge.
So for you, our listener, think about what you find most convincing. After hearing about the strengths and weaknesses of mathematical Platonism and all those other viewpoints, what's your take on the nature of math reality? And how does that affect your own philosophical work on epistemology and metaphysics? That's the question for you to ponder as you continue exploring philosophy.
We hope this deep dive has given you some good insights into this fundamental area of the philosophy of math and has sparked some more intellectual curiosity.
Thanks for joining us on the deep dive. Keep thinking about all this.